Bitwise operators will always consider the binary representation of operands before performing computations on them. Python provides 6 bitwise operators: bitwise AND denoted by single ampersand, bitwise OR denoted by a single pipe, bitwise XOR denoted by caret, left shift denoted by double lesser than, right shift denoted by double greater than, and one's complement denoted by a tilde. Bitwise AND works on the principle that it looks at all the bits, and if it finds at least one of the bits to be 0, then it outputs the result as 0. If all the bits in consideration happen to be 1, the result happen to be 1. Now, what Bitwise AND will do is, let me just erase the output and try to explain this to you. Bitwise AND will consider the corresponding bit positions. So we are performing a bitwise AND on the variables var1 and var2. The first thing that it does is, like all bitwise operators do, they consider the binary representation of the numbers. So the first number, my first operand 12, is stored in the variable var1. So what bitwise AND will do is, it will first consider the binary representation of 12. Now, don't think that all integers are represented using 4 bits. No, it's not the case. In Python, remember, all integers are represented using 32 bits. Now, I have used 4 bits only for explanation and representation purpose. Of course, it would be very difficult for me to represent 32 bits and then explain things to you. That's why I've used the minimum number of bits required to represent a number in base 10. So here I have the number 12. Now, the first thing, like I mentioned, you consider the binary implementation or the binary representation of 12, and that happens to be 1100 using 4 bits. But again, like I said, 12 is actually stored using 32 bits. So what happens to the remaining 28 bits? The remaining 28 bits, which are present on the left side of the 4 bits that you see here. So the 4 bits are 1100 that I have shown you here. The remaining 28 bits, which are to the left of the 1, which is at the leftmost position that I've highlighted right now, the remaining 28 positions are filled up with zeros. So you have 28 zeros here. You have 28 zeros followed by these 4 bits. Okay, so that's how it works for all examples that I have taken here. Remember, all integers are represented using 32 bits, but for representation purpose, I've used only 4 bits, and the remaining 28 bits are actually stored using zeros. They're padded with zeros on the left. Okay, now let's come back. So we'll consider the corresponding bit positions. So the rightmost bit position in var1 is considered with the rightmost bit position in var2. Now, if you perform a bitwise AND, what are you getting? You're getting a 0 and you're getting a 1. So since there is a 0 in one of the positions, the result will be 0. Now, consider the next corresponding position. So you have a 0 here in var1 and another 0 in var2, like I have highlighted. So a 0 and 0 will give you a 0. Now you have a 1 in the next position in var1 and another 1 in the next position in var2. So 1 and 1 will give you 1. And in the last position, the leftmost position in var1, you have a 1. And in the leftmost position in var2, you have a 0. Now, since you have a 0, again, the result is 0. So this is the 4-bit representation. 0100 is the 4-bit representation for the number 4. So if you output this, you get 4 as the result, which is the binary representation resembling 0100. So this is how bitwise AND works. Now, bitwise OR, just like in bitwise AND, will first consider the binary representation and proceed to look at the corresponding bit positions. So first we'll consider 0 and then we'll consider 1. So what is 0 or 1? 0 or 1 will be 1, because how does bitwise OR operate? Bitwise OR operates on the principle that all the bits that are taken into consideration, if any of those bits, if any of the bits that we are taking into consideration happen to be 1, then the result is 1. If all the bits that are taken into consideration, if all of them happen to be 0, then the result is 0. So you're looking for at least a single bit, 1 in order to get an output 1. Now, if you look at the first position, you have a 1 in var2, so you get the result as 1. Now, if you look at the second position, second corresponding positions in var1 and var2, you have a 0 in var1, you have a 0 in var2. So all zeros, the result is 0. Now, in the third position, you have a 1 in var1 as well as a 1 in var2. So you get two ones. At least one binary digit 1 is required. So that suffices. Two ones, even better. Now, another 1 in var1, doesn't matter what is there in var2. So the result is again 1. Now 1101 happens to be the binary representation of 13. So the result of this should be 13. And exactly that is what we get. Now, the next bitwise operator is bitwise XOR. Now, how does XOR operate? XOR looks at all bits as input given to it. And if it finds an odd number of binary 1 digits, it outputs 1. Otherwise, it outputs 0. So, if you look at the first position, in var1 it's 0, in var2 it's 1, so you have a single 1. That means you have an odd number of ones. So the output will be 1. If you look at the second position, you have a 0 in var1 and you have a 0 in var2. So in this case, you have 0 ones. 0 is an even number. That means you have even number of ones. So the result should be 0. Again, look at the third position. You have a 1 in var1 and you have a 1 in var2. Again, you have two ones. So even number of ones. The result will be 0 because you will get a 1 as your output in bitwise XOR only if you have an odd number of ones. Now, if you look at the fourth position, you have an odd number of ones because you have a 1 in var1 and you have a 0 in var2. So 1 XOR 0 is 1. So the binary representation 1001 represents the value 9. So the result should be 9, and that is exactly what we get. So that was bitwise XOR. Now coming to bitwise left shift and right shift. Now bitwise left shift has the significance that it is equivalent to the multiplication operation. Remember this bitwise, yeah, you can call it bitwise left shift. So bitwise left shift is equivalent to multiplication. Now, how does this multiplication take place? If you look at this value here, now you have the bitwise left shift. Now on the left hand side of the left shift operator, you have the variable var1 which holds the value 5, and on the right hand side of the bitwise left shift you have the value 1. Now whatever you have here, in this case you have a 1, you may have 2, you may have 3, you may have any value. Whatever is the value, that is taken into consideration for multiplication. So if I tell you that you have x left shift y, it is same as x into 2 to the power of, so you know that the power of operator in Python is double star, so it is same as 2 to the power of y. So in this case, the example that I've shown you here, the print statement that you see, it's var1 left shift 1. So here the y, so what is x? If you just compare, if you compare this expression that I've commented out, the part that I've highlighted right now, if you compare this with the expression that you have inside the print statement, you can get a fair idea. If you compare, you find that x is var1, which is nothing but 5, and your y is 1. Now what is happening? You're doing an operation of x to the power of, if you look at this, x into 2 to the power of y. So what is x? X is 5 into, that is multiply by 2 to the power of y. What is y? Y is 1. So 5 into 2 to the power of 1. That comes out to be 10. If you had, instead of 1, if you had 2, then what would have been y? Y would have been 2. So it would have been 2 to the power of 2. Now what is 2 to the power of 2? 2 to the power of 2 is 4. So 5 into 4 is 20. So if you print this, you get 20 because I changed it to 2. Now if I bring it back to 1, you will get 10. Yes, exactly. That is what you get. Now, if you look at an interesting part here, if you have, so this was the binary left shift. So even if you have negative numbers, I'll come to right shift in a moment. Even if you have negative numbers and if you try to left shift it, no problem. You see, you get minus 50 into 2 to the power of 1 because this 1 is on the right side of the left shift operator. So you get minus 100. Okay. Now, let's move on to right shift. Now, bitwise right shift is equivalent to division. Now, this division, mind you, is integer division. So, bitwise, bitwise right shift, remember, is equivalent to binary, I'm sorry, not binary, integer division. So, it is same as finding the quotient, right? It is same as finding the quotient of the division operation. Now here again, what happens is you will raise the value to the power. If you compare, so here, let's say you have x right shift y, it is same as x. Now remember the double slash represents integer division. So if you will have x double slash 2 raised to the power of y. Now here, if you compare again, just like we did in case of left shift, if you compare, you get, if you compare this expression that I've written here, the part that I've highlighted, if you compare this part, x right shift y, with var1 right shift 1, then what do you find? You find that x is equal to var1, which is same as 50. And you also find that y is equal to 1. Now, if you perform the calculation, what will you find? You will find x. So let me just comment this out. This is same as 50 integer division 2 to the power of 1. So what is 2 to the power of 1? It's 2. So 50 divided by 2 is 25. So the result that you will get is 25. Execute this, and that is exactly what you get. If I change this from 1 to 2, then what will happen? It will be 2 raised to the power of 2. So it will be 50 divided by 4. Now 50 divided by 4 will give you how much? 50 divided by 4 will give you a value of 12. Remember, the decimal part will be truncated. Now if you see, that is exactly what you get. You get 12. So since the decimal part is truncated, that is why I'm referring to this as integer division. So it is same as finding the quotient. So that is how the right shift works. And even for the right shift, we can consider negative values. So even if you perform a right shift on a negative number, the division will take place. So here you get minus 25 because you're right shifting by one position, and that is same as dividing by 2 to the power of 1. So dividing minus 50 by 2 to the power of 1 will give you minus 25. Now, after we are done with the conventional left shift and right shift, there is one important thing to note. If we try to shift, see, we can shift negative numbers, right? Like we have seen here, we shifted minus 50 to the right, we even shifted minus 50 to the left. All's fine. But if we try to shift by a negative position, then we will get an error. Have a look. If I try to execute this, I get a value error saying that there is a negative shift count, this minus 1. Since I'm trying to shift a value by minus 1 position, that doesn't make any sense. So I'm getting a value error saying that there is a negative shift count. This part on the right side of the right shift operator, this is called the shift count. Now the shift count cannot be negative. If it is negative, we'll get a value error like we can see here. And this is the same thing. Now this is the same thing with right shift. Even if we try this with right shift, we'll get the same error, right? We get the negative shift count error because we cannot shift a number either to the left or to the right by any negative position. Okay, so in the previous case we saw that we were trying to shift it to the left by negative position. Now we are trying to shift it to the right by negative position, so it doesn't work. Now what we find is the last bitwise operator, the last bitwise operator is the ones complement operator, right? Is the ones complement operator. Now what ones complement does is it simply inverts the bits. So zeros will become ones and ones will become zeros. Now if you want to find the binary representation of any number in base 10, you can use the bin function. So here I've used the bin function. I'll just give you a demonstration. If I execute this, I find that the binary representation happens to be 1010. Again, the representation that you see here is using minimum number of bits. Once again, I'll repeat that the number of bits used to store integers in Python is 32 bits. Here only 4 bits have been shown. The remaining 28 bits are present to the left and are padded with zeros. So the remaining 28 bits are present to the left of this representation that you see 1010, and they are all zeros. So this is called padding with zeros. Okay, now this 0b that you see here, this is only for representation purpose, only to give us a hint that this 1010 is a binary number. So this 0b tells us that 1010, this these 4 bits 1010, they represent a binary value. Okay, so this is how you can find the binary representation. Now if I try to find the ones complement, what I'll do is I'll simply apply the tilde and then I'll give the name of the variable, but I'll not be able to give you the exact result because remember we are dealing with 32-bit representation. Simply simply inverting these bits will not give you the exact answer. You will have to invert all 32 bits, starting from the leftmost position till the rightmost position. Here we have shown only 4 bits for representation purpose. So to get the exact result, what you can do is you can write down the 32 bits and then keep on inverting. The zeros will be converted to ones and the ones will be converted to zeros. However, remember, negative numbers are stored in Python using 2's complement. So whatever value that you get, the negative of it, if it is a negative number, then it will be stored using 2's complement. Okay. So that was all about bitwise operators in Python. Let's quickly recap what we learned from this video. We started off with the names of the bitwise operators. There were 6, like you can see on your screen. We saw how bitwise AND works, where all bits have to be 1 in order to produce a 1 as the output. If any of the bits happen to be 0, then the result is 0. In bitwise OR, all bits, if are assigned to a bit value of 0, then the result is 0. If any of the bits happen to be 1, then the result is 1. Okay. In bitwise XOR, if you have an odd number of ones, then the result is 1. If you have an even number of ones, then the result is 0. Bitwise left shift is significant because it is equivalent to multiplication. So the multiplication happens by positions which are raised to the power. So if you are performing an x left shift y, then it is same as multiplying it by 2 to the power of y. Right shift is equivalent to integer division, where if you're doing x right shift y, it is same as dividing by 2 to the power of y. Now we can shift negative numbers as well. We can shift negative numbers to the left as well as to the right, like we have seen in these two examples where we tried shifting -50 to the left by 1 position, and that was same as multiplying it by 2 to the power of 1, so that gave us 100. Similarly, we tried shifting a negative number -50 to the right by 1 position, and that was same as dividing it by 2 to the power of 1. So dividing -50 by 2 to the power of 1 rightly gave us -25. Another thing that we noticed was we cannot shift a number, whether positive or negative, by a negative number of positions. So I tried shifting 50 by -1 positions, which doesn't make any sense, and that's why we got a value error. And this was true for right shift as well as left shift. In order to find the binary representation using minimum number of bits of any number given in base 10, we have to use the bin function. So the bin function would give us the binary representation, like we can see here. The variable var1 has a value 10, and its binary representation using minimum bits is 1010. Only for representational purpose, we have this prefix of 0b, which tells us that 1010 is a binary number. The final bitwise operator that we had to explain was the ones complement operator, denoted by a tilde. Now, if we perform ones complement on a variable, what we get is the zeros inverted to ones and the ones inverted to zeros, although we don't get the exact answer here because all numbers are represented using 32 bits. If you have to get the exact answer, then we'll have to consider the 32-bit representation and then perform the inversion operation. So here it's not possible to demonstrate the exact answer. Like I said, if you find time, you can note down the 32-bit representation of the decimal value 10 and then find its equivalent ones complement. And remember, negative numbers in Python are stored using 2's complement method. If you found this video useful, do give it a thumbs up and subscribe to our channel. If you have any doubts, please feel free to leave them in the comment section below. I hope you found this video useful, and I'll see you in the next one. Thank you.